So today we're going to start moving into molecular structure. We're going to wrap up atomic structure using what we know about where electrons are positioned and the number of valence electrons, the most important attribute of an atom as we start to move into molecules. And so what we're going to do is start by drawing molecules as Lewis dot structures, and then we're going to progress into more modern ways of depicting molecules, things that are approaches that are more practical and useful and still used every day. Okay, so Lewis dot structures. Lewis dot structures are one of three methods of drawing molecules. And what it really utilizes is it's a method that, or a method of representing atoms. Where valence electrons are drawn as little dots around the atom. And this word is drawn, excuse me, sorry about that. Okay, so for example, let's look at the most simple example, and that is hydrogen with a zero charge. So if we had hydrogen with a zero charge, we could put a 1. The atomic mass isn't super relevant here. We just need to know the total number of electrons that we're dealing with, and we're going to only consider the valence electrons as we're depicting these things. So if you recall from a previous lecture, you may already know how many valence electrons are in the neutral element hydrogen because it's in group 1. Right? It's a group 1 element, which says that it should have 1 valence electron. Now, if we look at this, we've actually already figured out how many valence electrons it has when we looked at the total electron count, because the hydrogen atom only has electrons housed in the 1s orbital, that s orbital in the first shell. So if it only puts electrons in the first shell is actually its valence shell, and those electrons are its valence electrons, in this case 1 electron. So we have 1 valence electron. Okay, we figured that out. So now if we have a Lewis dot structure, for 1H0, it would look like an H atom, the atomic symbol, plus a dot for each valence electron. So the atomic symbol, which you could also think of as the atomic letter, I guess, the atomic symbol, and a dot for each valence electron. So that's hydrogen, an H with a dot. H for hydrogen, dot for its 1 electron. The thing we want to do as we move into other elements is we don't want to forget the various rules. In particular, we don't want to forget the Pauli exclusion principle and Hund's rule. A little sloppy there. Exclusion and Hund's. So we don't want to forget the principle and the rules as we're drawing more complex Lewis dot structures. Let's look at an example of that right away. So our favorite element, carbon, and we'll pick on the neutral carbon, I guess, carbon 12, 0 charge. I'll write it this way. It's good practice. Okay. So carbon 12 with a 0 charge has how many electrons? It has 6 electrons total. Not all of those are valence electrons because some are in the first shell, some are in the second shell. We recall that it's a group 4 element, or you could write out the electron configuration 1s2, then 2s2, 2px1, 2py1, 2pz0, for example. And we would see that we have 4 valence electrons. Okay, so what we want to kind of think about is something a little bit strange. I know that when we look at the electron configuration, we like to put 2 electrons into the s orbital, but we're actually going to spread the electrons out all over the carbon atom to prepare for bonding. So as we look at converting these atoms and their Lewis dot structures into molecules, we want to spread the electrons out as much as possible to prepare for bonding. Okay, so for carbon, what that means is we're going to have 4 sort of spots around the carbon atom where we're going to put 1 dot, as opposed to, and really, this isn't so incorrect, because if we're thinking about the atom sitting by itself, maybe you want to do something like this, and you say that 2 of the electrons are paired up maybe in the s orbital. The s orbital is lower in energy than the various p orbitals, so we could put one in each of the p orbitals, so we have 2 electrons sitting by themselves, but then we have 2 electrons paired up in that s orbital. I can't really say that you're too incorrect, but what we're going to see as we progress through our structures and these lectures and look at how atoms become molecules and how they bond together to form covalent bonds, we see something that's called orbital hybridization, where orbitals that were once different in energy, like the s and the p orbitals, mix together to become equal in energy, allowing us to spread the electrons out much more, and in effect kind of prepare for bonding and accomplish bonding. So what I'm getting at is between these 2 Lewis dot structures, I like a Lewis dot structure where we spread the electrons out more for carbon. Now, that might seem confusing, I understand it. It will be until we get a little bit of practice, but the nice thing is there's not too many elements we're going to play around with. It's for the most part going to be hydrogen, carbon, and these other 2 elements. So we have nitrogen 0, we could do the same analysis. I'm going to remind myself that that's a group 5 element. We would see that in the periodic table. So we have 5 valence electrons. Now, what's interesting is as we spread the electrons out to prepare for bonding, what we're going to notice, and there's good reasons for this, but just suffice it to say at this point, what we're going to notice is we don't really have more opportunities than 4 in terms of coordinating atoms to bonding to other atoms to our atom of interest. So we have nitrogen. We can only really bond at most 4 other elements to it. So we only have like 4 spots around the atom to put electrons. I like to think about it as just north, south, east, and west that we can hold electrons. So what I'm getting at is we've got electrons to the west, to the east, to the south. What about to the north? Here we're going to fit not 1, but 2 electrons. These electrons are paired up. Okay. Some alternatives you could think about are, and hopefully what I kind of alluded to, something like this, where we've got electrons spread out as much as possible. That doesn't really work, and we'll see why that doesn't work in other lectures, but this is not a possibility for us because we can only have 4 atoms. So only position electrons in 4 spots around the atom. Okay, so you can't spread them out more than 4. You can't have 5 spots to put electrons. As soon as we get up to 4, we're going to start to see things pair off. Okay, another alternative possibility you could consider is let's put 2 electrons to the south, 1 electron to the west, east, and north. This is okay. This is okay. So these 2 possibilities are okay. You could put 2 electrons to the west, 1 electron to the east, north, and south. Conversely, 1 electron to the east, 2 excuse me, 2 electrons to the east, then 1 electron to the north, south, and west. Okay, so you can move the paired electrons around the atom, but we want to just not exceed the number of 4. Okay, so there's a Lewis dot structure for nitrogen. What about oxygen 0? Oxygen 0 is in group 6. So it has 6 valence electrons. Now what we see is if we have 6 valence electrons, oh, that is an ugly O. Okay, 6 valence electrons, we can put 1 electron to each of the north, south, east, and west. We've spread them out as much as possible. And then what we can do is we can put the last 2 electrons, we can pair them up at any position, so long as we don't exceed 3 electrons at any one position. Okay, so each position that is north, south, east, and west, these are Willoughby terms, I guess. So each position can hold 0 to 2 electrons. We want to spread the electrons out as much as possible. So situations where we have 0 electrons, that would be like hydrogen, where we just had the 1 electron, then we could put it anywhere north, south, east, or west, but we don't have any more to add, so we can't have any paired electrons in that particular atom. For oxygen, though, we have 2 pairs. Those 2 pairs could each be positioned in various places. The last group are the halogens. So the halogens would be chlorine, bromine, iodine, and fluorine. Halogens all have something in common, and that is they have 7 valence electrons. 7 valence electrons, and if we look at how to position those, we'll pick on chlorine. Now, it doesn't matter how many total electrons it has. We go right to group 7. That's the halogen group. We know that it has 7 electrons. I'm not going to worry about all the other electrons, just the valence electrons. And for chlorine, bromine, iodine, and fluorine, we're going to put 1 electron in each of the positions, but we still need to fill 7. So 5, 6, 7. As an example, you can move the 1 unpaired electron at any position so long as the other spots are paired up. So we have here 7 dots total. Sorry about that. My pen stopped working for a second. Let me get the notes back in front of us. Okay. So the notes are back in front of us. We have chlorine with its 7 dots. We have oxygen. And really, these are the only elements we're going to work with as we build up molecules. There's another important group, though, that is the noble group, the noble elements. These elements are characterized by having 8 electrons around or in their valence shell, so 8 valence electrons. And since we can only put electrons at 4 positions, north, south, east, and west, each of the 4 positions is going to be paired up to get us to 8. Now, another caveat as you're drawing Lewis dot structures of elements is that we kind of want to have the elements, the electrons as close to the atomic symbol as possible. So sort of, I'm going to just write here, bad technique would be if we had neon, for example, and if we put electrons kind of spinning out. Instead, we want those pairs flat, pressed up against the atom. So this is kind of a quick and dirty look at drawing Lewis dot structures of atoms. In future lectures, we're going to look at something called the octet rule and how that allows us to see how these individual atoms can bond. And hopefully we can make sense of why we have electrons, instead of pairing up into s orbitals and leaving a p orbital vacant, for example, we have these electrons sort of spreading out around the atom as much as possible. Okay.